This is Moiz Khan from MTS4B. In today's video, we will be giving you a quick introduction to computing, and this introduction and basic topics that we will be covering today is from the course of microcontroller and embedded system. Let's start. So the topics we will be covering in today's video are internal organizations of computer, different parts of computer, which is input and output, memory and CPU, how to connect these different parts with the computer, connecting memories to computer, CPU, connecting input and outputs, and how a computer works. Internal organization of computers. So basically the input and output. What is input and output components? The keyboard, mouse, sensor, these are the input components of a computer, and the output component is basically a display of the it's basically a display of your work. For example, an LCD printer, hands of a robot. These are all the output to show your work. Memory. What is a memory? Everything that can store, retain, and recall information is a memory. For example, a hard disk. In terms of technology, there is hard disk and SSD. In terms of just understanding, a basic piece of paper on which you write something is also an example of memory because it contains a specific data and piece of information. There are different types of memories and memory characteristics. So what are the basic characteristics of a memory? The capacity, how much data can it store? In terms of technological memory sticks, the capacity, the unit for storing capacity is bits, the number of bits that a memory can store. That is the capacity of that memory. For example, 200 and 128 kilobits and 256 megabits. These are all the capacitive units. And as you can see in the PowerPoint slide, each row on the right side has 4 bits, and there are total of 128 locations. That means we will have to multiply 128 by 4, which will give us the total capacity of that specific said memory. The access time. What is access time? Basically the amount of time required to extract that piece of data or information from a memory to the computer is called the access time. A good memory stick will basically have less access time, and a bad memory stick will take large amount of time for the extraction of that data. Different types of memories, semiconductor and non-semiconductor memories, we will be studying this in the future. So basically the types of memory, that is ROM, ROM and RAM. Read only memory is on the left and random access memory is on the right. So the read only memory sticks are used to basically store data, and the random access memory sticks are used to basically process the data. There are different types, as you can see on the PowerPoint presentation. Mask ROM, PROM, EPROM, double EPROM, Flash EROM, and on the RAM side, SROM, DRAM, NVRAM. These are all the different types of ROM and RAM. We will be discussing it. So the mask ROM, programmed by the IC manufacturer. These are the types of random only memory types on which the manufacturer or the programmer only needs to program it once, and after that he does not require to basically reprogram it, and he basically cannot reprogram it after one time, only be programmed once. For example, a toy car manufacturer will only program the chip inside it once, and after that, the output will be generated on the specific program that the IC manufacturer put in it during the first time. The PROM is one time programmable. You can program it only once, just like the um, mask ROM. After that, there is EPROM, erasable programmable ROM. This is a very old technology, EPROM or EPROM. So basically, in this type of ROM, you can shine ultraviolet radiation lights to erase the data inside the stick. Basically, this is a very old technology. Erasing takes up to 20 minutes. The entire contents of the ROM are erased. Basically, you cannot specifically delete specific contents inside the stick. Basically, once you delete it, all the contents inside the memory are deleted at once, and it takes basically 20 minutes or up to 20 minutes. So basically, this is an old technology. Moving forward, there is double EEPROM, electrically erasable programmable ROM. Basically erased electrically, instantly erased, and each byte can be erased separately. So this is a new technology in which each byte, each specific type of data can be erased specifically and instantly. So this shows us that this is new technology. Flash ROM, erased in a flash, the entire device is erased at once. Moving towards RAM, there are different types of RAM: static, dynamic, and non-volatile RAM. Static RAM made up of flip-flop transistors. Advantages: this is faster, no need for refreshing. Disadvantages: high power consumption and expensive. So these are made up of transistors. There are obvious advantages and disadvantages. This is faster. It does not require basic refreshing, and the disadvantages is it is expensive and high power consumption. And these are all the characteristics of a static RAM. Moving towards the dynamic RAM, these are basically the opposites of the static RAMs. These are made up of capacitors. Advantages: that it uses less power consumptions, it is cheaper, high capacity, and disadvantages: basically it is slower and refresh needed. So one would prefer the static RAM over a dynamic RAM. Moving towards the non-volatile RAM made of SRAM, static RAM, battery controlled circuitry. Advantages: very fast, infinite program slash erase cycle, and non-volatile. Disadvantages: it is expensive. So as compared to the static RAM and non-volatile RAM is preferred. Tasks. It should execute. So basically now moving towards forward, why do we need a CPU? What kind of tasks can a CPU provide? Or what basically is the basic requirement of a person? Why does one buy a CPU? So there are different tasks that a CPU helps us execute. It should execute instructions. It should recall the instructions one after another and execute them. Connecting memory to a CPU. So in a CPU, there are different components that are attached or connected to a CPU. Memory is one of the components, and it is attached. So in a memory pin out, the diagram is shown. There are different components inside of a memory, different pins. The DO is the data output, the AO is the address output. Basically, the data output will this pin transmits the data read from the memory cell when a read operation is initiated. Next one is AO, that is the address output. This pin outputs the memory addresses that is being assessed. The WE1 is write enable. When this pin is activated, usually set to low logic, it signals the memory chip to perform a write operation. The output enable, the next one, this pin controls when the data on the DO pin, which basically the data output pin, is valid, essentially enabling the output buffer for reading data. Next one, the last one is CS chip select. This pin selects which memory chip on a circuit board should respond to a certain address and data operation. Basically, this chip select is kind of a manager that will tell the all the above pins that which one of them is enabled and required. Moving forward, there is a CPU connected to the memory. There is a CPU connected to a memory, and this shows that the data output can move in both ways from CPU to the memory, and the address output can only be initiated from the CPU to the memory. So the data output can go both ways, and the address output will only go from CPU to the memory because the address is stored in the memory. So whenever the CPU requires a address, it will go to the memory, and data goes both ways in the CPU and in the memory, so that can shift from left to right as shown. Next is connecting inputs and outputs to a CPU. CPU should have a lot of pins because there are a lot of different controllers and input and output devices that are required throughout the different tasks in a CPU. Network, mouse, graphics cards, sound cards, speakers, or gaming controllers, anything that is that you want to use with your computer needs to be connected. These are all the things that you need to manually or physically connect to the, these are the things that you cannot connect via Bluetooth or any other thing, you know. So the graphic, basically a graphic card, you have to physically connect the pins of a graphic card to a CPU, just like the sound card which is required to provide sound to the CPU, the keyboard, the mouse, these are all the things that are connected via pins. How is the connectivity pattern or a diagram is shown to represent how the connections of a CPU are made. There is an address pad for there is an address bus, data bus, and control bus. So with each pin, there is a code to each pin, like 0, 1, 2, 3, first pin, second pin, third pin, zeroth pin, and n shows for the total amount of pins. And the input and output components are connected to each pin or the specific pins. The address bus is followed in each input and output pin, just like the data bus and control bus. The control bus here will tell us how which one is which program and which pin should be enabled. So what is a control bus? A control bus in memory refers to a set of electrical lines within a computer system that carries control signals. So that is the purpose of the control bus being here. So now we have connected different input and output devices to our CPU, and other than that, we will also connect a memory stick to our PCU. Sorry, CPU. Uh, in this slide, there are different connections that are shown, and the question is, how could we manage it? How can we manage all these visual lines that are shown in the power slide? So basically, what we have to do is we have to individually select one component and attach it to the other one. So this is a very complicated thing, but in today's world, these things have been um configured accordingly, and it had been made easier for the user. So what in today's world, what we do is, instead of a control bus, as you can see here, is a logic circuit. Instead of the control bus, that's purpose is to read, write, and read. So instead of that, we will just use a logic circuit. And how can we make the logic circuit? We will tell you before telling you the basic definition of a logic circuit. The logic circuit enables the CS when addresses is between 0 and 15. Yeah, the 0 and 15 are hexadecimals basically, and the logic circuit is an alternate, or instead of these control buses, we use a logic circuit. How do we basically make a logic circuit? The steps are following. Write the address ranges in binary. Separate the fixed part of the addresses. Using a NAND gate, design a logic circuit whose output activates when the fixed address is given to you. Basically, a logic circuit is also like a managing circuit that will basically address to the specific or that will enable the specific address that the CPU requires. So making it, basically, first we have to translate the requirement into the binary. Let me take you directly towards the example. There's an example later on in the slide that I'm gonna just jump towards. So yeah, this is the example. Design an address decoder for an address 300H to 3FFH. Basically, these are the addresses are given in hexadecimal. First, we will write these hexadecimal addresses in binary. So the binary for 3, because this is 300H. H is for hexadecimal, and basically the address is 300. So the binary for 3 is 0011, as you can see here, and the rest are 0. Next is 3FF. So the binary for 3 is 0011, and for F is 40. So there are two Fs. So 1111 for first F, and another quadra ones for the second F. So here we have now converted the hexadecimals into binary, and now the second step is to separate the fixed part, the common part. So here the fixed part is the first two rows and the first four columns. There is 00, 0 0 1 1 and 1 1. So for the zero representation, there is a circle. As you can see here, this circle basically represents a zero. There are two columns of zero, so we will use two circles and two columns for one. So we will use two pins. The pins represent the ones and the circles represent the zero. Just give me a minute, guys. Okay, so it has been 15 minutes. Okay. Moving forward, inside the CPU, there are different components inside of a CPU. There is a PC, program counter, instruction decoder, ALU, arithmetic logic unit, and registers. Basically, the ALU, the arithmetic logic unit, in the green as shown in the PowerPoint slide. The ALU is required to do all the mathematical calculations. The instruction decoder is used to basically decode the data in a easier form, and the registers basically the registers are there to basically handle each situation with respect to their codes. The A register, there are different types of registers: A, B, C, and D. These are the specified designations, and one by one, each of these registers will be given a specific task which will be completed by them. And the program counter basically shows the which specific task is on the counter. Basically, if the third task is on the counter, the program counter will show 4 because it starts from binary. Let's move forward. So here we now have an example of basically how a computer works. On the right side, on inside the memory, there is data that will show us the basic functions and basic instructions inside the memory that we have to execute. And the inputs and outputs are connected with the CPU. So is the memory stick. So all these things are connected, and now we have to perform a specific task, which is according to the set of functions or data stored in this memory. Let me zoom in for you. So basically, there are total of 8 tasks in that memory, or 8 designated data oriented programs inside of a memory that we have to execute. So basically, let me give please give me a second. Okay. So the first, basically on the zeroth location, basically the blue paper here shows the literal meaning of the operation, and in the left, on the left table, basically this is the computer language on the left, and basically just for our understanding, on the right it shows us the literal command of what the process is. So the first on the zero, there is said that 31H is on the zero. On towards the next slide, the program counter will be on 1 from 0 to 1, and the number 31 will be on the here. So next up, it says A17. That means the 17th input output will contain a specific data, that is 9. So basically, on the address bus here, the A17. So on the from the 17th input, because that is what's being enabled. So from here, the address bus will be on 17 because that is the address on the memory, and the 17 input is has given us a data which is 9. So that 9 will now travel towards A, because on the 17th input pin there is a component that is giving us a data which is 9, and here the operation says that move the 17th input component's data to A, and A here is the register. So this 9, which is the data on the 17th input pin, will now travel to A on the next slide, as you can see. So was an example of how all these things operate and coordinate with each other. So next operation is A and B. So basically, whatever was stored in the A register will now move to the B register. So this 9 will now move towards the B register, and this A register will now become empty. So this is how the basic operations work inside of a computer. Uh, on this slide, basically, these are instructions to how a decoder works. So there are two architectures in this slide. The Von Neumann and the Harvard architecture. Basically, this is like a block diagram, or this is like a pathway diagram that shows you how the data travels within a specific computer. The core memory, for example, can only travel to the CPU, and the the data bus and the data memory, these can go both ways. The data bus can go towards the CPU and the data memories, just like the address bus. As discussed before, the address bus can only go to the data memory, not towards the CPU, just like the control bus. So these are basically the architectures to show you. This is like a diagram to show you the directions of how the data can travel, and in what ways the data can travel within these components. Now moving forward, general purpose of microprocessors or microcontrollers. Microprocessors, there are no RAM, ROM, input, output ports on the chip itself. Basically, in a microprocessor, there is only a processing chip. All the other things are now, all the other things on a microprocessor are connected individually. That it does not contain any RAM, ROM, time, as you can see in this diagram. And instead, there is a microcontroller. In a microcontroller, all these things, all the ports, all the pins of a RAM, ROM, input, output, and the cores, the processor, all these advanced RISC machine, all these things are basically joined together in a singular chip, rather than connecting all these things individually. As in the microprocessors, in the microcontroller, all these things are joined and assembled together in a single chip. You can also watch for yourself in and help yourself explaining this diagram. Moving forward, these are all the basically these are all the links from which you can get a better understanding. Embedded systems. An embedded system is controlled by its own internal microprocessor or microcontroller as opposed to an external controller. A PC is connected to various embedded products such as keyboard, printer, modem, disk controller, sound card, CD-ROM driver, mouse, and so on. A printer gets data and prints it. A mouse takes coordinates and sends to the PC. Basically, all these things show you how the different components inside of a computer coordinate with each other to execute a specific set task from us. Embedded products, there are different types of embedded products in different fields: computing, cars, communication, and cards. In computing, there is PC, notebook, laptop, storage, color printers. These are all the embedded products in the field of computing. In cars, there is anti-lock braking system, ABS, airbags, engine control, transmission control, climate control, collision avoidance. Basically, the sensor, the rear parking sensors, or the front collision sensor. These are all the embedded products that are used in the car industries. Communication industries, the components, the embedded products in the line of communication are wireless phones, cellular phones, PDA, pager, fax machine, intercom. In terms of cards, banking, electronic purse, social security, and toll. These are all different fields in which different products in of embedded products are used. These are also examples. Choosing a microcontroller, what are the characteristics that one thinks of while choosing of a microcontroller? That there is speed, packaging, power consumption, RAM, ROM, timers, input, output pins, cost, availability, compiler, simulator, and debugger, availability of that specific chip in the market. So these are all the things that needs to consider before choosing a microcontroller for itself. The AVR microcontroller family, this is another basic architecture. That the basic architecture of AVR was designed by two students of the Institute of NTH. So, but what is it? The AVR stands for Advanced Virtual RISC or ELF and Vanguard RISC. The AVR is an 8-bit RISC single chip microcontroller with Harvard architecture. RISC and CISC. CISC is complex instruction set computer. A large number of instructions, typically from 100 to 250 instructions. Some instructions that perform specialized tasks and are used frequently infrequently a large variety of addressing modes, typically from 5 to 20 different modes, variable length instruction formats, and an RSA reduced instruction set computer with relatively few instruction, relatively fewer addressing modes. So basically, an CISC is a complex instruction set computer in which this computer is used to perform a large amount of instruction and needs to execute a large amount of tasks. On the other hand, the RISC is used is given a few set of instructions and informations and a few set of addressing modes, and the work done also, or the execution, the tasks required for the RISC to complete are respectively low or small in terms of the CISC. Harvard and von Neumann architecture, as discussed before, these are the detailed architecture plans of the Harvard and Neumann. The AVR microcontroller, this is also the block diagram or an easy way or simplified view of the AVR microcontroller. As you can see, there is a program flash ROM connected to the CPU and data buses, OSC interrupt unit. These are all the parts that are connected to the CPU. And this is a simplified view of an AVR microcontroller. This right here might seem confusing, but these are all the simply. This is the simplest way of making you understand or getting a better understanding of the AVR microcontroller. So one can easily understand the concepts of AVR microcontroller by just having a single look at this diagram. The AVR family, the AVR can be classified into four groups: 32-bit, X mega, mega, and tiny AVR MCUs. These are different classifications of the AVR family: 32-bit, X mega AVR. These are all written in detail. Let's get familiar with the AVR part number 80, X mega